Welcome to our deep dive today. We're going to be tackling a real head scratcher, especially for philosophers. It's all about the implications of Einstein's famous E equals mc squared.
Ah, yes. E equals mc squared. Definitely more than just a physics equation. This one really kind of pokes at the very nature of reality, doesn't it?
It really does. And we're using some pretty heavy-duty sources today, excerpts from the Stanford Encyclopedia of Philosophy's entry on, get this, the equivalence of mass and energy. So yeah, we're like prepping for a grad seminar with some seriously brainy thinkers.
Exactly. Imagine we're explaining all this, to a fellow philosopher. What are the subtle points, the different ways to interpret it, the questions it raises about, I don't know, existence itself? That's kind of our mission today.
I love it. Okay, so to set the stage, let's rewind a bit to the pre-Einstein days, Newtonian physics. Back then, mass was pretty straightforward, right? Like how much stuff an object had.
Yeah, it was like the classic quantity of matter view. Twice the force needed to move it at the same speed. Well, that means twice the mass. It was all about inertia.
Makes sense. But even back then, there were some hints of trouble brewing. Folks like Ernst Mach were already kind of questioning if that whole quantity of matter idea really captured it all.
Right. Mach was really onto something. I mean, he was pointing out that defining mass by how much other stuff it pulls on, well, that gets kind of circular, doesn't it? It was like a hint that maybe, just maybe, our intuitions about mass were a bit too simplistic.
Like we were missing a piece of the puzzle.
Mm-hmm.
And then boom, enter Einstein with his game-changing equation. And, most people know it as E equals mc squared, but, to be precise, it's actually E sub O equals mc squared. What's the deal with that little O?
Ah, great question. That little O there, that stands for rest energy. It's the energy something has just by existing, even when it's perfectly still. See, E is total energy, and that includes kinetic energy and all that, but E sub O is purely the energy that's like locked up in its mass, just sitting there.
So like my cup of tea here, even though it's just chilling on the table, it has this hidden energy reservoir thanks to its mass just because it exists.
Precisely. And then you've got, that's the rest mass, measured when the object's not moving. And finally, c squared, the speed of light, squared, a huge number. And that emphasizes just how much energy is packed into even a tiny bit of mass. It's really mind-blowing when you think about it.
The universe is shouting at us saying, hey, matter is way more energetic than you think.
Exactly. Now, here's a common misunderstanding, something we need to clear up right away. E sub O equals mc squared. This equation, it isn't about literally converting matter into energy like some kind of sci-fi transmutation.
Okay, yeah, I can see how people might get that impression. So what's the deeper meaning then?
It's all about the relationship between changes in rest energy and changes in rest mass. So if an object's rest energy increases, well, so does its mass. And vice versa, of course.
Okay, so like if I heat up this tea, it technically gets a tiny bit heavier because it has more thermal energy, right?
You got it. The Stanford Encyclopedia actually gives this really wild example. They say accelerating a battery to 670 miles per hour, that takes the same amount of energy as fully charging it. But the mass increase from just charging it, it's only 1 part in a million million.
Wow, that is wild. You wouldn't think everyday actions like charging a battery have anything to do with this grand equation.
But they do. It highlights how interconnected energy and mass are, even at these seemingly mundane levels. It's everywhere.
It makes you look at the world a little differently. Now, if an object has all this energy kind of bound up in its mass, where exactly does it reside?
Oh, that's a great question. And as the physicist Wolfgang Rindler pointed out, the answer kind of depends on how deep you want to analyze the object, how deep down the rabbit hole you want to go.
I'm always up for going deep, so lay it on me.
All right, well, it could be in the thermal motion of molecules, the energy stored in chemical bonds, or in the excited states of atoms, or even within the nuclei themselves. A significant chunk actually resides in the mass of those fundamental particles, and that can be released in very extreme cases like matter-antimatter annihilation.
So it's like describing a city, right? You can talk about its overall energy consumption, or you can zoom into individual homes, or even further down to the appliances within each home.
That's a perfect analogy. The level of analysis, that's what determines where you kind of locate that energy. Let's take an example, the example of an ideal gas in a container. Now, heating it up, that doesn't actually make the molecules themselves any heavier individually. But the system's total rest energy, and thus its mass, that does increase because the molecules are zipping around with more kinetic energy, right? More motion, more energy.
So it's the energy of the system as a whole that's crucial here, not just the individual parts.
Exactly. That's a great insight. And this brings us to I'd say, the philosophical heart of the matter. How do we interpret what E sub O equals mc squared means about mass and energy?
Yeah, this is where things get really interesting, especially for a philosopher, right?
Absolutely. And there's no single agreed upon answer. Physicists and philosophers, they have different takes on what this equation tells us about the nature of these things, about mass and energy. It's not as cut and dry as you might think.
Ooh, intrigue. So give me the rundown on these competing interpretations. What are we looking at here?
All right, well, one view is that mass and energy, they're fundamentally the same thing, just measured in different units. And that emphasizes the kind of the unification that relativity brought about, but it might feel, I don't know, counterintuitive to our everyday experience, like they feel different.
Yeah, like saying water and ice, they're different forms of the same substance, H2O.
Perfect analogy. Now, then there's the view that they're distinct properties, but what we call conversion, that's just energy changing forms, like potential to kinetic. And this works well for many cases, but it struggles with reactions where particles seem to just, poof, disappear entirely.
So it's like saying apples and oranges are different, but you can still make juice out of both. But those vanishing particles, that's where things get a little spooky.
You said it. And that leads to another interpretation. Distinct properties, but conversion is possible at the fundamental particle level. This one's the most cautious view, sticking closely to what relativity actually tells us without making any extra assumptions.
So acknowledging the mystery, but not jumping to conclusions.
Right. And finally, there's this thing called Lange's one property view, named after the philosopher Mark Lange. And he claims that only mass is actually real. And what we see as these apparent conversions, they're just illusions caused by shifting our level of analysis. It's pretty radical. It highlights how our perspective kind of influences what we observe. But it raises some big questions about whether reality itself should be dependent on the observer.
Whoa, that's like saying only the ingredients of a cake are real, and our perception of a whole cake is just a convenient illusion.
You got it. It's a very thought-provoking perspective for sure. It questions some of our most basic assumptions about physical properties.
Mind-blowing. All these interpretations. It's like E sub O equals mc squared is like a philosophical Rorschach test. Everyone sees something a little different in it.
I like that. It speaks to the power and the depth of this equation. It's not just about physics anymore. It's about our understanding of reality itself. And speaking of understanding, how did Einstein even arrive at this equation? That's a big one.
Yeah, it was a bolt from the blue, years of toiling away, something else entirely. Spill the beans.
Well, you see, he actually had multiple ways of deriving E sub O equals mc squared, each with its own philosophical implications. Some used Maxwell's theory of electromagnetism. Others were purely dynamical, meaning they didn't rely on any specific force.
Wait, so you can get to the same result through totally different paths. That's kind of wild. What does that tell us philosophically?
Well, it suggests that mass-energy equivalence, it isn't just a consequence of how light behaves, which is what those electromagnetic derivations might imply. The purely dynamical ones, they show that it's baked into the very structure of space-time according to relativity. It's deeper than just light.
Okay, my brain's trying to catch up here. How does
Yeah.
how does space-time itself lead to E sub O equals mc squared? I need like a relativity crash course.
All right, well, think about it. In Newtonian physics, momentum is mass times velocity. Pretty straightforward, right? But special relativity, it introduces this thing called relativistic momentum. And that takes into account that as something approaches the speed of light, its mass effectively increases.
Okay, so the faster something moves, the harder it is to push it even
Yeah.
further, right? Like trying to sprint through, I don't know, increasingly thick molasses.
Yeah, that's a great analogy. And just like we have relativistic momentum, we also have relativistic kinetic energy. Now, to derive E sub O equals mc squared dynamically, you kind of have to redefine these concepts, these energy and momentum concepts, in a way that's consistent with relativity, but also works like the old definitions at low speeds, so it all fits together.
It's like building a bridge between Newton's world and Einstein's world.
Precisely. And once you have those relativistic definitions, then you can start to analyze collisions in a whole new light, literally. Imagine two objects colliding, and you're observing them from two different viewpoints. One where the total momentum is zero, we call that the center of mass frame, and another that's moving relative to that first one.
Hold on, what's this center of mass frame thing? I'm not sure I follow.
Sure, so imagine you're, I don't know, floating in space, watching these objects collide. The center of mass frame, it's like finding that special spot where the collision looks perfectly balanced, as if neither object is carrying more momentum than the other.
Okay, I think I get it. Like
Yeah.
the perfect neutral observer viewpoint. So back to those two viewpoints.
Right. So by applying the conservation of energy and the conservation of momentum in both of these frames, and using our fancy new relativistic definitions, the math, it just spits out E sub O equals mc squared.
Wow. It's like the equation was hidden within those basic laws all along, just waiting for relativity to come along and unlock it. Pretty amazing.
It really is. It's a beautiful example of how, these seemingly simple principles can lead to really profound consequences. Like Galileo once said, the book of nature is written in the language of mathematics, and E sub O equals mc squared. Well, that's a particularly elegant sentence in that book.
I love that. Speaking of elegance, are there any kind of subtle but important details within E sub O equals mc squared that we might miss at first glance? Anything we should pay close attention to?
Yeah, there are actually. Remember how we talked about the possibility of exotic matter, stuff that might have mass but not be convertible into energy? That's a wrinkle that people often overlook.
Right, right. The idea that maybe there's some weird matter out there that doesn't play by the usual rules. So do we just, like, ignore that possibility?
And not ignore, but from a practical standpoint, physicists generally assume that, all matter is ultimately convertible into energy. And this is based on a ton of experimental evidence, but it's important to acknowledge that it is an assumption, not a proven fact.
Gotcha. So it's like a working hypothesis until we find that black swan of exotic matter.
Exactly. And so far, all signs point to E's O equals mc squared holding true across the board. No exceptions found yet. Now, this kind of raises a deeper question. If it's so fundamental, this equation, shouldn't it have some kind of ontological implications? For what exists, for the very nature of being, that kind of thing.
Okay, now we're getting into the really juicy philosophical territory I was hoping we get here.
Right. So you see, E sub O equals mc squared. This equation, it's made us really rethink that traditional distinction between matter and fields. Remember, in classical physics, matter was the stuff. It had mass, it took up space, while fields, they were kind of intangible. They were these things that mediated forces like gravity.
Okay, so like my table here, that's matter, but its gravitational pull on the Earth, that's through a field.
Right. And fields, they were thought to have energy, sure, but no mass. But then E sub O equals mc squared comes along, and it kind of blurs those lines. If mass and energy are equivalent, and fields definitely have energy, doesn't that mean that fields have mass too?
Whoa. So those invisible fields are more real than we thought. Like they're not just some abstract concept.
Exactly. And this has led to some pretty radical interpretations. I mean, Einstein himself, along with Leopold Infeld, they suggested that maybe the universe's fundamental building blocks aren't matter or fields, but some kind of hybrid entity that can be either or, can shift back and forth.
Like a cosmic Play-Doh that can be shaped into different forms. Sometimes it looks like matter, sometimes like a field, but it's all the same stuff deep down.
I like that, a fun way to visualize it. And philosopher Eliezer Zahar, he went even further. He argued that mass-energy equivalence implies this fundamental I know not what, some underlying reality that we can't even fully grasp with our current concepts, Like we don't even have the words for it yet.
Okay, now we're in deep metaphysical waters. It's like saying the universe is made of something we don't even have a name for. Pretty humbling.
It is humbling, isn't it? Even with an equation as profound as E sub O equals mc squared, we're still just, peeking through a keyhole at the true nature of reality. But let's not forget, all this theorizing, it needs to be grounded in real-world evidence. It can't just be philosophical speculation.
Right, it can't just be a thought experiment. So what's the experimental proof that E sub O equals mc squared is actually true? How do we know this isn't just some mathematical fantasy?
Well, it all started with a bang, literally. Back in 1932, John Cockcroft and Ernest Walton, the pioneers of, atom smashing, they provided the first experimental confirmation.
Atom smashing, that sounds intense. What did they do?
They built one of the first particle accelerators. It's a device that smashes atoms together at really high speeds, allowing them to study the nuclear reactions that occur. Like, what comes out the other end?
So they were like the heavy metal rock stars of physics, just smashing things up to see what they're made of.
I like that analogy. So in one famous experiment, they bombarded lithium atoms with protons. And what they found was that the products of the reaction, these two helium nuclei, they had a combined mass that was actually less than the original lithium atom and proton. Some of it was gone.
Wait, so some mass went missing. Where did it go? Like, vanished into thin air?
Well, that's the key. It wasn't missing. It was converted into energy. just as E sub O equals mc squared predicted. That missing mass, it reappeared as the kinetic energy of those helium nuclei. And Cockcroft and Walton, they measured this energy and it matched the equation perfectly.
That's incredible. Seeing this, abstract idea actually come to life in a real-world experiment must have been a huge eureka moment.
Oh, it definitely was. It was a turning point. It proved that mass could indeed be converted into energy. But the story doesn't end there. As technology advanced, physicists designed even more precise experiments to really put E sub O equals mc squared to the test, make sure it held up under scrutiny.
So what are some of the later experiments that really put this equation through its paces? Like the best, the best?
Well, one standout is from 2005. A team led by Simon Rainville, they directly measured the energy released in this nuclear reaction called neutron capture.
Neutron capture, that's where a nucleus absorbs a neutron, right? Becomes a little bit heavier.
Exactly. And it releases energy in the form of gamma rays, those super powerful, high-energy photons.
Okay, and where does E sub O equals mc squared come in? How does it relate to this?
Well, according to the equation, the energy of those gamma rays, it should precisely correspond to the mass difference between the original nucleus and the heavier one that's formed after it captures the neutron. Like, the energy should match the mass change perfectly, and that's exactly what Rainville's team found.
Wow, so they nailed it. And just how precise were they?
They confirmed E sub O equals mc squared to an accuracy of 0.0000004%. Incredibly precise.
0.00004%. That's insane. It's like measuring the Earth's circumference with an error smaller than the width of a human hair.
It's a real testament to the power of both theoretical physics and incredibly meticulous experimentation.
From Newton's simple mass to Einstein's mind-bending equation and then its experimental validation, we've covered a lot of ground in this deep dive.
It's been quite the journey, and it really makes you appreciate the power of these fundamental equations to reshape our entire understanding of the universe, doesn't it?
Welcome back to our deep dive. As we wrap up exploring the philosophical implications of E sub O equals mc squared, it strikes me that one of the biggest shifts it brought is in our understanding of mass itself. Like, it's not just about how much stuff an object has anymore, is it?
You're absolutely right. It's way more than that. You see, in Newton's world, mass was this simple absolute property. But Einstein showed us that, well, mass is relative to the observer's frame of reference.
Okay, so the faster something moves relative to me, the heavier it appears to be. That's where that whole idea of relativistic mass comes in, right?
Exactly. Relativistic mass is basically the mass of an object as measured by someone who's moving relative to it. And the closer an object gets to the speed of light, the more its relativistic mass seems to increase, like it's getting heavier and heavier, approaching infinity.
So if you could somehow actually reach the speed of light, you'd have infinite mass. That's just mind-blowing.
Well, theoretically, yes, but there's a catch. Special relativity tells us that nothing with mass can actually hit the speed of light, because it would take an infinite amount of energy to accelerate it that fast.
Ah, so there's a cosmic speed limit. Unbreakable, even with all the energy in the universe. Pretty cool.
It is pretty cool, isn't it? Now, while the concept of relativistic mass can be useful sometimes, it can also be a bit misleading. It kind of reinforces that old Newtonian view of mass as just stuff, just more of it at higher speeds, but that's not really the whole picture.
So how should we think about mass in the context of relativity? If relativistic mass isn't quite right, what is?
Well, a lot of physicists nowadays, they prefer to focus on rest mass instead. That's the mass of an object that's measured in its own rest frame, when it's not moving.
So it's like the object's intrinsic mass, the mass it has, regardless of how fast it's zipping around relative to someone else.
Exactly. And rest mass, that's a truly fundamental property in special relativity. It stays the same no matter who's observing it or how fast they're moving relative to the object.
That makes a lot of sense. So even if an object's relativistic mass appears to increase as it approaches the speed of light, its rest mass is always constant.
Right. That's the key takeaway here. And this is where E sub O equals mc squared comes full circle. This equation, it tells us that this unchanging rest mass, it's directly proportional to the object's rest energy.
So even when something seems perfectly still, like my cup of tea here, there's this huge amount of energy locked up in its rest mass, all thanks to E sub O equals mc squared.
You got it. And this is one of the most profound implications of this equation, really. It forces us to reconsider our very notion of what constitutes matter, like what it even means.
It's a real game changer, for sure. We've gone from this simple view of mass as just stuff
Yeah.
to a much deeper understanding of its connection to energy and its relativistic nature. But what does it all mean, like, for the big philosophical question? What is mass, really?
Ah, that's the million-dollar question, isn't it? And it's one that continues to spark a lot of debate among philosophers of physics. Some argue that mass is fundamentally a measure of an object's inertia, its resistance to being accelerated, how much it fights back against change.
So it's not about how much stuff something has, but how stubborn it is about changing its motion.
That's one way to put it. Others suggest that mass, it's actually a manifestation of how energy curves space-time itself, according to Einstein's general theory of relativity.
Huh.
It's a whole other can of worms.
Whoa, so mass is like a ripple in the fabric of space-time. That's getting pretty deep.
It is. And then there's the view that mass and energy, they aren't even fundamentally different at all, but just like different aspects of a single underlying reality. Kind of like those ontological interpretations we were talking about earlier.
Wow, it seems like the more we dig into E sub O equals mc squared, the more everything seems connected. Mass, energy, space-time, the nature of reality itself.
Absolutely. And that's what makes this equation so endlessly fascinating to explore, even all these years after Einstein first came up with it.
It really is. Well, it looks like we've reached the end of our deep dive into the philosophical depths of E sub O equals mc squared. It's been a wild ride.
It has. It's been a real pleasure exploring these mind-bending concepts with you.
Likewise. And to our listeners, we encourage you to keep questioning, keep exploring, and never lose that spark of curiosity. The universe is just brimming with mysteries, and E sub O equals mc squared, well, it shows us just how powerful human ingenuity can be in unlocking those mysteries. So until next time, keep those brains buzzing.
Until next time.